Hello. Good evening, class. I am Mohit, and in today's class, I'll be solving the problems which belongs to the block theorem and the tight binding model. So let me share the screen. Okay. So these are the previous year problems which I am supposed to solve. There will be 10 problems. I'll be going one by one. If any of you have the doubt, you can always write it in the comment section. I'll be happy to address your questions. Okay, let's start. The first question says that the delta ij at the Dirac delta function is 1 if I is equals to j and is 0. Otherwise, whenever the I is not equals to j, the function will take the value 0. Now the question asks that okay, what will be the value of summation over ABC is equals to 1 from 1 3 del AB, del BC and del CA. So this is an easy problem. So this function is such that it's 1 for I is equals to j, 0 for I not equals to j. That's what the question is. Now the question asks what is ABC is equals to 1 3 del AB, del BC and del CA. So this is like, you can think like if you take it in the 3 dimension, then you can write it as del AB, del BC, del CA, X plus del AB, del BC, del CA, Y plus del AB, del BC, del CA, Z. These are the 3. So I write this 3 in terms of X, Y and Z. You can write it in terms of 1, 2 or 3. Anyone is fine. Or you can write this X is equals to 1, Y is equals to 2 and Z equals to 3. This is also fine. That's what this equation means. Now for A is equals to B is equals to C, del AB, del BC, del CA will be equals to 1. Right? Other else del AB, del BC, del CA will be 0. Therefore, equation 1 will be 1 for A is equals to B is equals to C, 1 plus 1 plus 1, this will be equals to 3. So the correct option will be the 1. So that's the answer to the first problem. That for A is equals to B is equals to C, the summation in 3 summation for 3 such values will be equals to 3. Now let's move on to the next problem, which is for an electron moving through a one-dimensional periodic lattice of periodicity A, which of the following corresponds to an energy eigenfunction consistent with Bloch theorem? Okay. So what the question says is that there is an electron which moves in a periodic lattice of periodicity A. Let's say that these are the lattice points crystal in which the electron is moving, and this spacing is A. That's what the question says. Now it says that which of the following corresponds to an energy eigenfunction consistent with Bloch theorem? Okay, so for Bloch theorem, wave function, we know that psi x plus a will be equals to e to the power I k a psi x. This is the condition for the Bloch theorem. That's when an electron move in a periodic lattice, then its wave function will be at any point x plus a, where a is the is a point in space A. It will be equals to e to the power I k a psi of x. That's what the wave function will be. Now let's see which of the functions satisfies this condition. Start from first. Start from 1. So psi x plus a will be equals, psi x is given a, that's the normalization factor, exponential of iota pi x by a plus cosine of pi x by 2a. So this is the psi x. Now psi x plus a will be a exponential of iota pi x plus a by a plus cosine pi x by 2a, and x will be replaced by x plus a. So let's just solve it. Psi x plus a will be a exponential iota pi x by a plus pi by a times a. Let me write it only pi plus cosine of pi x by 2a plus pi by 2. So cos 90 plus theta will be minus sine theta, right? So it will be a exponential of, let me take out I pi outside, I pi, then exponential of I pi x by a minus sine pi x by 2a. If you compare the equation 1 and 2, suggests that option number A, option A doesn't satisfy Bloch theorem. It satisfies the Bloch theorem. Now let's look at the option number 2. Option number 2 is psi x a exponential of I pi x by a plus cosine 2 pi x by a. Psi x plus a will, so let's call this equation 3. Psi x plus a will be a exponential of I pi x plus a by a plus cosine 2 pi x by a plus 2 pi psi x plus a. I can write it at a e to the power I pi exponential of I pi x by a plus cos 2 pi plus theta will be cos theta cos 2 pi x by a psi x plus a e to the power this. If I can write it at like this, right? E to the power I pi times a. So this is nothing but psi x. So I can write it like e to the power I pi psi x and psi x plus a will be nothing but e to the power I pi by a times a psi x, and I can write it as e to the power a k a psi x. This satisfies Bloch theorem, so it is a valid solution. Now moving on to problem number 3, option number C, that is psi x. We call it at equation number 4. Option number C, that is psi x a e to the power I 2 pi x by a. Two pi x by a. I cos hyperbolic 2 pi x by a cos hyperbolic equation number 5 x is so this is cos hyperbolic x, right? E cos hyperbolic x is nothing but e to the power x plus e power minus x by 2. Now let psi x plus I cos hyperbolic. Cos hyperbolic is nothing but e to the power 2 pi x by a plus a plus e to the power I a psi x plus a e to the power exponential I 2 pi by a times x plus 2 pi plus e to the power 2 plus iota e to the power I 2 pi. So this is like, you cannot write it in terms of psi x, right? There will be some phase effect. There will be some additional plus a, and here it will be minus x plus a. So you cannot take out just uh, either x a or something. So in that case, it will be, you cannot write it in block form. So it is also not a solution. Also not a block solution. So the correct answer is second. Now moving on to problem number third, which says that which of the following statement is not correct about the Brillouin zone of a square lattice with a lattice constant A. So the question says that it is a square lattice so this is a square lattice so I'm just drawing like a square lattice. Okay, so this is square lattice which I have drawn. These black circles are the lattice points. Now let's address the question. The first Boolean zone is a square of side 2 pi by in kx ky plane. Okay, this is my, if my lattice is square in square with lattice constant a, then Brillouin zone lattice vectors will be 2 pi b cross c times a dot b cross c. Right? This is what it is. So if it is like in x and y, so your a will be a times x cap, b will be b times a times y cap, and c will be 1 times z cap unit vector. So this implies your this will be your kx. Let me write it better. So that b1 will be 2 pi a2 cross a3 divided by a1 dot a2 cross a3 a1 a2 and a3. So the b1 will be 2 pi a2 cross a3 will be nothing but y cap cross z cap will be x cap, and a1 dot this will be This will be ax cap, and then this will be a square. This implies 2 pi by a x cap. Similarly, b2 will be 2 pi by a y cap, and b3 will be 0 z. It will be 2 pi by a1 a square times a square. This is 2 pi by 1 z cap. So this is just a constant in a unit vector. So the first Boolean is the square of side 2 pi by a in kx and ky, right? In kx and the ky, it is 2 pi by a. So basically, this will be 2 pi by a x cap, and this will be 2 pi by a pi cap. The areas of the first Boolean zone and third Boolean zone are the same. Okay, this I'll have to show you that how they are same. So if I just copy it, if I copy. So let's just construct the first Boolean zone, second Boolean zone, and third Boolean zone. How do we construct the first Boolean zone? We join the nearest neighbors. And then we bisect it, perpendicular bisect it. This one also we bisect it. This one also we bisect it. And this one also we bisect it. So this is my first Boolean zone. Now to make second one, how do we do it? We join the line with the second nearest neighbor. This one is the second nearest, root 2a. Now we will bisect it also. If you bisect it, it will be so this will be my second Boolean zone. Now if I want to make third Boolean zone, how do we construct it? We make it to the third nearest neighbor. Then we bisect it. If we bisect it, it will go like this. So this is third one. So if you just do some little bit of math, and this is the area. If consider this area, this will be a square. First Boolean zone area will be 2 pi by a times 2 pi by a. That will be 4 pi square by a square. If you these four triangles are there, right? These four triangles are there. So you can shift this one here, this one here, this one on the bottom, and this one on the top. So this will also make this will also fill this thing, right? So let me just show you what I mean. Right? So let me just do it like this. Let me just copy it. So this is one. Copy, paste. This one will go and fit in somewhere here, like this. So these are not, I have not made it perfect, but it will fit this region. The other will be like this, this top region. The other will be like this, and this is how you can do it either, or you can just calculate the area, and the area will turn out to be the same for each of the Brillouin zone. That will be the 4 pi square by A. It will be 4 pi square by A if you calculate the area. Yeah. So the first Brillouin zone is square of side 2 pi by A in kx, and yes, this is right. The area of the first Brillouin zone and the third Brillouin zone are the same. Yes, this is also right. The k points are equidistant in kx and ky. Yes, you can see that kx, these points and these points are equidistant by 2 pi by A. So yes, this is also true. The area of the second Brillouin zone is twice that of the first Brillouin zone. No, this is false. Area is same. So problem number 3 is also solved. Now let's move on to the problem number 4, which says that which of the following can never be Wigner side cell for any two-dimensional Bravais lattice. So square, if you have a square, the square lattice which I drew in the next class, last class, uh, previous problem basically. So here, so this is a, this is also a, this square lattice. So if I take, so Wigner side cell is the primitive cell containing one lattice point, right? So in the square lattice, yes, you can choose, for example, you can choose either this one. How do you choose it? You make the line this, and this, then you bisect it, and you make this Wigner side cell. So this is the Wigner side cell for the square one. So this is true. That square can have the 2D Bravais lattice, right? In the rectangle, yes, this is also true. Let me show you rectangle. If this is rectangle, then let's just bisect it in section, and what we will get will be this, this, and this. So this will be the uh, Wigner side cell for the 2D Brillouin lattice. Now the hexagon. Let me just if it's a hexagon, then in that case, in hexagon it has at the center also, and then copy, paste, copy, paste. So this is, so how do you do it? You, the nearest neighbor distance is in every atom is a, so you just connect it, and then you bisect it. This, this. So this is the the Wigner side cell for the Brillouin lattice. Now the pentagon, the option number 3. The pentagon, the lattice is like this. So this is the pentagon lattice. In this, it is not possible to choose because the nearest neighbor distance is not constant. It's changing. Like you cannot choose the points which you can bisect and make a Wigner side cell. It's not possible to make Wigner side cell in pentagon lattice. So the option is third. Now, so this is this problem. Now coming on to the problem number 4, 5. That given the energy dispersion of the foam, we know that this dispersion form comes when you take the nearest neighbor hopping to be the T, and E naught is the ground state energy when there was no hopping when T was 0. So now if you bring the closer and allow the hopping to come, if the dispersion turns into the E naught minus 2T cos theta, where the solution is of the term UMA e to the power in theta plus B e to the power im theta. Now, for periodic boundary condition, the periodic boundary condition is like this. You have a lattice and then repeatedly here. So let's say this is your Q1. This goes up to UN. Then you have this UN plus 1, and then the same thing continues. So for periodic boundary condition, U1 will be equals to UN plus 1, and if you say U0, the atom which is just before this one, so there will be something like this also, right? Will be equals to UN. This is equation 1, 2, 3. Substitute 2 in 1. So u1 will be a e to the power I theta plus b e to the power minus I theta is equals to a e to the power I n plus 1 theta plus b e to the power minus I n plus 1 theta. Let's just do it. A plus b e to the power minus I theta I 2 theta. Let's divide by 2 I theta. Then it will be a e to the power I n theta plus b e to the power minus I n plus 2 theta. Let's call this equation number 4. Now substitute 3 in 1. A plus b is equals to a e to the power I n theta plus b e to the power minus I n theta. Compare equation 4 and 5. b1 minus e to the power minus I 2 theta is equals to b to the power minus I n theta 1 minus e to the power minus I 2 theta. So this implies e to the power minus I n theta is equals to 1. This implies and theta is equals to 2k pi times theta is equals to 2k pi by n. Let's see if there is an option like this. Yes, option number 4, 2k pi by n. So that is the correct response for this question. Now coming on to the problem number 6. For a nearest neighbor tight binding model in 3 dimensions, the bandwidth is okay. So if it is in 3 dimension, time model is in 3 dimension, right? The bandwidth. So we know that the energy dispersion, this is from the class notes, you can refer, and from the previous problem also the expression is written. You can see that E is equals to E naught minus 2t cos theta. So I will just write that thing only. That's dispersion relation. E is equals to E naught minus 2t cos ax plus cos ky ay plus cos kz az. There will be states like that below the cos kx ax plus cos ky ay plus cos kz az, and above that also the 2t times this factor. So you can think it like this is your E naught and bandwidth. So this is your top state, this is your bottom state, and this is actually your bandwidth. Here E naught is 0. That's given in the problem. And t is equals to minus 1. So if t is equals to minus 1, then we all know that if t is equals to minus 1, that it will be, let's just substitute. E is equals to E naught plus 2 cos kx plus cos ky ay plus cos kz az. Right? So this in the bottom state. Bottom state will be when kx ax is equals to ky ay equals to kz is equals to, they had to be -1. So it will be 2n plus 1 times pi here, and belongs to integer. So, so bottom state energy will be equals to E naught plus 2 times -3. This implies E naught is 0 already. So this will be -6. Similarly, top state will be when kx ax equals to ky ay is equals to kz az is equals to 2 and pi. Here n belongs to integer. So the energy will be, for this one, the energy will be 6. This implies the bandwidth will be, let me call this E2, let me call this E1. E2 minus E1 is equals to 6 minus 6 is equals to 12 will be the bandwidth. Is there any option like 12? Yes, there is an option. So 12 will be the correct option for the bandwidth. Okay, so this is the problem. Now moving on to the problem number 7, that for low energies near the Dirac point, which of the following is true about graphene? Okay, so the problem is about graphene. So we know that graphene lattice is something like this. Right? This is the graphene lattice. So this here the point which I'll be labeling, this point, and this point are of one kind because they share one kind of environment. And the point which are like this and this, they share one kind of environment. Okay, let me describe what does environment mean. Look at this point. It has 2 points like in the neighbor like this, and the third on the bottom. But and similarly, this one has this, and this in the bottom. But if you look at this point, this one is up, down 2 arrows, 1 up arrow. But here it has 2 up arrow, 1 down arrow. So they are like 180-degree to each other. If you rotate them by 180 degrees, then they are like, so these 2 points are different, and this kind of degeneracy in the system is called the pseudo spin. And it, like in analogy with the spin, one calls it the pseudo spin. So the graphene has, along with the spin degeneracy of 2, gs is equals to 2, it has gk, which is the spin degeneracy, k and k prime. They are the 2, so total degeneracy is 4. So the graphene band has 2 distinct. Okay, let's not talk about the spin right now. It's more about the what are the different kind of distinct points. So the point which are the labeled in the purple and the blue, they are the different. So there are two distinct points, and the dispersion relation for graphene. Graphene, which is a 2D material, honeycomb lattice, is E is equals to H bar K Vf plus minus. So the dispersion relation of graphene is like this, linear dispersion, where Vf is 1 into 10 power 6 meter per second. If you compare it with the dispersion of E is equals to Pc, I can write, right? P is H bar K is my P, and Vf is like this. So this is like the Dirac dispersion. This is linear in K, and it has two distinct points. So if I can't draw it in 3D, but if I show you it in 3D, then it will be like the 6 points where it touches, and these three. One second. These three will be of one kind, and these three will be of one kind. They are known as valleys and pseudospin valley, whatever you call. One is known as, this is like K prime. So you name them in the usual convention to name these are the K and the K prime. So these two value, and if one breaks these value physics, one can get the anomalous signal, and all those things are there. So the quantum anomalous Hall effect, if you want to realize those phenomena in the system, you have to break the value degeneracy in the system. That's what the sense of these values are. So the correct answer is the graphene band structure has two distinct points, and energy is equals to K. Energy proportional to K. Proportional to K square comes for the bilayer, two layers of graphene. Bilayer graphene. This is for graphene. Six distinct points are not there because these three are of similar one. They are similar, same. So there are only two distinct points. Now moving on to the next problem. The band energies for the conduction electron in a tetragonal crystal is given by, okay, the band dispersion is given. Ek is h bar square by 2 m1 kx square. I can write it like this: h bar square by 2 m1 ky square plus h bar square by 2 m2 kz square. So I can write it like this, right? H bar square by 2 m1. Let me just call 2 m1 by h bar square is equals to a1 a 2 m1 is equals to b also, and 2 m2 by h bar square is equals to c. Okay, it's the first. So I can write the ek is kx square by a square plus ky square by b square, where a is equals to b, plus kz square by c square. A is equals to b but not equals to c. That's what the essence is here in the question. Now for sphere, a is equals to b is equals to c. Hence, not right. For tetragonal, you have the like this, the cubical kind of the thing structure. So this is also not possible. Okay, ellipsoid. Option number third. Ellipsoid equation is x square by a square plus y square by b square plus z square by c square is equals to some constant. So this is ellipsoid. If you compare this is equation 1 into a, and in the case of the ellipsoid, a and b and c can be equal or cannot be equal. So there is no such constraint. If you compare 1 and 2, this implies given dispersion is ellipsoid. Right? The fourth option is toroidal. For the toroidal one, the equation is somewhat different. This is for toroid. We are told that the ellipsoid is a right answer, but I will show it for the toroid also. The toroid is not the correct answer. Toroidal. It will be x square plus y square plus z square plus r is any constant. Small r is also constant. It will be 4r square x square plus y square. Right. So if you compare equation 3 with 1, toroidal is also not a right solution. Right? So this is the answer for this problem. Now moving on to the next problem, which is the following is the correct possible choice for lattice vector for graphene shown below. A is the distance between the carbon atoms. So A1 and A2, the question is asking. So this is something which we have showed in the previous assignment also. So I will refer to that. I will take up the values from there. This one we have solved. Okay, so how do we solve? So how we solved it was in this is the previous assignment problem which I solved in the previous assignment. You can refer to it. So the question says that A is the lattice length. So I defined it at 0, 0 and A 0. Now if this is 0, 0, I draw a line like this. So this is 120 degree. Here it will bisect it. It will be 60. This is 30. I do the cosine of 30 degree will be A by A. This gives me this height. It will be root 3A by 2. Then I can calculate this x also. So this is A by 2. So A plus A by 2 will be 3A by 2. So this I know 3A by 2. So this point I know that this point here corresponds to x is equals to 3A by 2. So the x is 3A by 2 here. This is A and here it's 3A by 2. This is A, this is 3A by 2. So this will be minus A by 2 because this is 0. Now the height also I calculated root 3A by 2. So this will be root 3A by 2. If I draw like this, I know that this angle will be 60 degree. Then I do the calculation B1 and B2. So this will A, the coordinate of this will be A and root 3A because I know the height of this one, root 3A by 2. So this will be root 3A and this is 0. So this will be A root 3A of this point. This point is minus A by 2 minus root 3A by 2. So that's how we calculate the B1 vector. 3a by 2, root 3a by 2, and b2 will be 3a by 2 minus root 3a by 2. The correct options here looks like to be the second one, 3a by 2 minus root 3a by 2, because here they have the a1 on the down and the a2 on the top. So this is like, or b2 and b1, and a2 will be root 3, the 3a by 2 and root 3a by 2. So this is root 3a by 2, this one. So the correct option here will be second one. Now moving on to the last problem, which is choose the correct option for properties of the graphene. Graphene has extremely high mobility. Yes. Graphene has extremely high mobility. Experimentally, like one has observed like 10 lakh volt meter second inverse, volt per meter second inverse. Huh. So this experimentally has been done, like the device which I make in my experimental lab, they are also of this mobility. So this is like very good mobility. Now the second option is graphene has lowest electrical resistivity among known material. Experimentally, if you ask me, no. Experimentally, there are better conductors, but if you ask me theoretically predicted is 10 power minus 16 and 10 power minus 8 for gold, silver, all those ones. So if you see theoretically, it has been predicted that it is very good electrical conductor, and maybe this will be achievable if one can optimize the fabrication technique with the graphene. Then maybe you'll be able to see these kind of resistivity. Hopefully, already graphene resistivity has improved a lot in the past 5-6 years. Graphene is highly impermeable, right? So the particles cannot permeate through graphene. The region being graphene lattice constant. So this length is 1.42 angstrom, and this is, yeah, this is 1.42 angstrom, and so, and the molecule size of hydrogen is 2.9 angstrom, helium is 2.8 angstrom, O2 is 3 angstrom. So they cannot pass through it. So it is like a shield which don't allow the molecules to pass through it. If they can't pass through it, it's highly impermeable. So the all are correct. The correct answer is third, that all are correct in this case. So that's what the answer is. So let me go over the problem which I solved in this assignment one by one again. That delta ij Dirac function is given, which is 1 and 0 if I is equals to j, else otherwise is 0. Then the summation over abc equals to 1 up to 3. Delta ab bc ca is equals to, so it's like in 3 dimensions you can take, and the summation over each of these for a is equals to b is equals to c will be nothing but 3. So the correct answer is 3. The second one is v for the for lattice like this, critical lattice, the block theorem says that psi x plus a will be equal to ika psi x. So we apply it on all the given functions, and we see that only the second wave function satisfies this condition. So this is the allowed eigenfunction for this kind of problem. The third problem is with the following statement is not correct about the Brillouin zone. The first Brillouin zone is square of 2 pi by n k x y k plane, right? We derived it like this. The area of the first Brillouin zone and third Brillouin zone are the same. Yes, all of the Brillouin zone areas are same. The k points are equidistant in kx as well as in ky direction. Yes, they are equidistant, as you can see here. This is also 2 pi by a, and this is also 2 pi by a. The area of the second Brillouin zone is twice that of the first Brillouin zone. No, this is false, because the area of the all Brillouin zone is same. You can calculate it also. Then we showed that the Wegener side cell for the given lattice is square is square, rectangle for rectangle is also a rectangle. For pentagon, it's not possible. For hexagon, it is a hexagon. That's what we showed here, that it will be a hexagon. For pentagon, it's not possible. Not possible. So the correct answer is pentagon. Then the energy dispersion of the foam was given E0 minus 2t cos theta. the solution form was also given. Then for the periodic boundary condition, we know that u1 will be is equals to whatever the function is u1 will be equals to un plus 1, and whatever is at u0 will be equals to un. So if we compute these ones, we get the theta is equals to 2k pi by n, which is the correct answer, number 4. For nearest neighbor tight bending model in 3 dimensions, the bandwidth is so E naught minus 2t cos kx. So for the 3 dimensions, so these one can take maximum value of 3 and minimum value of minus 3. So that takes 3 into 2 will be 6, and 3 into minus 2 will be minus 6. So the bandwidth will be the difference of these two, that will be the 12. Now the next problem was for the graphene. I showed that okay, these three points are of one kind and these 3 points are of one kind, rotated by 180 degree by with respect to each other. So there are the two distinct points, and energy dispersion for graphene is h bar kVf, where Vf is a constant known as the uh, velocity of the carrier. This is the velocity at which the carrier moves in the, so that it's like the Dirac particles. The electrons in the system are called the Dirac particles, and they don't carry the uh, that kind of they all move with a like a constant speed, that's 10 power 6 meter per second, unlike the massive particles. So they are massless particles. The band energy for the conduction electron was given for the tetragonal crystal. Ek is like this, so I wrote it in this form, and this matches very well with the ellipsoidal form. Now in the graphene, I showed that okay, what will be the A1 and A2 vector, just a mathematics, and that correct option is 2. In the last one, we showed that okay, graphene has extremely high electron mobility. Graphene has lowest electrical resistivity, theoretically 10 power minus 16 ohm meter, and graphene is highly impermeable because the bond length is very small. That's why it's highly impermeable, and so all the options are correct. So with this one, I will conclude the class. If you have any question or doubt, you can ask me in the comment section. I'll be happy to address your questions. हेलो, हाँ कहाँ पे भाई, आ रहा है क्या खेलने? तो ठीक है भाई. पे हो? ऊपर आओगे खेलने? ठीक है, मैं भी आता हूँ। नहीं, मैं आ रहा हूँ।